Hello, so in this video we're going to talk about different methods of integrating by parts, or different ways of representing how we integrate by parts. Now, the sort of standard method which will be shown will have involved using this formula. So if we're integrating u times dv by dx with respect to x, that's the same as doing u times v minus the integral v du by dx. Okay, and if you're doing an A-level exam in the UK, you are given this formula, so you don't have to memorize it. You can use it. It comes from the derivation. It comes from the product rule. But this is how this formula is how we try and integrate a product. If we're integrating something like x times an exponential, or x squared times sine or cosine, etc. So we've got a product of functions we're trying to integrate. We tend to look on integration by parts. Okay, now it's a bit of a funny one. Differentiation is a method that will just work. So if you have a product, you can differentiate something using the product rule, then it will definitely work. Integration by parts doesn't really work that well, depending on what the integral is. It just changes the integral to something else, which you might be able to work out, or you might not be able to. So it depends on what we can choose what our u and our dv by dx are. Now, in terms of making choices for u, we tend to rank them in a hierarchy, and we tend to use this what we call Lie8, or actually called late, so you might use something completely different than what you've been taught. So the first choice for u is always going to be logs. Okay, if you've got a log in the integral, normally you're going to be picking log as what your u is going to be, and then dv by dx will just equal other thing. Okay, so equals the other part. The other part of the product. Okay, I stands for inverse, so that's thinking about inverse trig functions, so inverse sine, inverse cos, and so on. It kind of counts logs, almost counts as the inverse of an exponential, so it kind of counts as well. Algebra, so that's your any terms that x squared, any powers of x, you pretty much are involved with that one. Trigonometry, so that would be sine, cosine, tan, sec, cosec, and so on. Last but not least, we've got exponentials. So anything we've got power, so e to the x, 2 to the x, 3 to the x, that would be right at our bottom priority. The reason for that is because in terms of difficulty of integrating and differentiating. So if I took e to the x, for example, well, it's really easy to just differentiate. But unless you know a trick, it's very hard. It's easy to integrate as well. Well, let's say log x, that's really easy to differentiate, we know what it is, but again, unless you know a trick, it's quite hard to integrate. So it's based off the difficulty and kind of how it makes next. So I'm just wobbling on here, but how it makes the next part. If it makes it simpler, if it makes it more complicated. So this is the typical sort of way of going along it. I'll also show you a tabular method which works for certain ones, but not necessarily all of them, but it might be helpful for you to see both methods and sort of make a judgment for yourself about how you feel about them. So we'll go through the main method and I'll show you another method as well. So standard example, we've got x times e to the x, we've got a product of two functions, we want to integrate them by parts. So let's think about Lie8 for our choice of u. Now we've got an exponential on there and we've got some algebra, we've got x in there. Okay, so what I'm going to choose, I'm going to say let u equal x, and then the other thing is dv by dx, which will equal e to the x. Now I've got to differentiate du by dx, so I'll differentiate x, so to x, get 1, integrate dv by dx, integrate e to the x, get e to the x. I do technically get a plus c, but you don't need to put it in here because it will cancel if you were to write it in, so it just adds a bit of effort and algebra in terms of what you're doing. So let's now apply the formula. So I'll write it back down so you can see how I'm applying it rather than just putting stuff down out of nowhere. So that's the integration by parts formula. So the way I remember it is we've got u times v, so that's x e to the x minus the integral v times du times nothing 2 together. Okay, and that's the same thing as the integral of x e to the x dx. Okay, remember to put your dx's in there, well, because sometimes the L examiners will take marks off for that. Okay, so now just carrying on, I've got x e to the x minus, now the integral of e to the x, really nice and easy, it's just e to the x, and then we just need to remember our constant at the end, r plus c, and that is our integral. We could also check this by differentiating it. So if I want to differentiate it, so we know I'm differentiating it. So x e to the x, if I differentiate that, product rule, differentiate the x, so I get just 1, plus differentiate e to the x, so I'll get that, minus e to the x, and if I differentiate c, that'll go to 0. Okay, they cancel, I'm left with x e to the x, so I know that we've done it correctly, or we found something that integrates something that differentiates to x e to the x. So this is probably the correct integral. So that's the standard way of doing it in terms of algebraically and applying the formula. So I'll now show you the tabular method. It's sometimes called the DI method because, well, tabular is in the table, DI because we differentiate and integrate alongside each other. Now we go through the same process of picking what u is. So if we think about Lie8, so that's what I'm going to differentiate. So I'm going to put x there. And the other thing I'm going to integrate is going to put e to the x. Because of the minus sign of formula, we're going to write next to it some alternating signs. Plus, minus, and that pattern would carry on. If I were to differentiate x, I'd get 1. Differentiate 1 and get 0. If I differentiate 0, I'd get 0. And I could keep going on, but I'm just going to keep writing on 0, so it's pointless. If I were to integrate e to the x, I would get e to the x, get e to the x, get e to the x. So on the sort of d side, I'm differentiating, on the I side, I'm integrating. Now all I do is I times going diagonally. Okay, so here I'm going to get x e to the x, and it's positive, we've got a plus here. Now this one here, it's basically like I've got a minus. So minus 1 times e to the x is minus e to the x. And I'll get 0 from everything else. So actually the point where you get 0, you can basically stop. And what I've got here is my integral, x e to the x minus e to the x. All I need to remember is my plus c, as before. If you look, that gives me the same answer as I had here. So it's another way of representing it that might be a bit easier for you to manage. So do practice both methods, however, because as we'll find out, that second example, the DI method, doesn't work for certain integrals. But we'll go through a few in this video. So let's do x squared sine x. Now this would be one where we might have to repeat our integration by parts, and actually this is one where the DI method is very straightforward. So I'm going to show you how I do it using the DI method first, actually here. Draw a line relatively straight, which actually can't. So just thinking about Lie8, logs, no, inverse, no, algebra, yep, so x squared is going to differentiate, sine x is going to be what we're going to integrate. And then just remembering our sine. So actually I'm just going to differentiate that with 2x, differentiate that with 2, differentiate that with 0. Stop that. We've got our alternating signs. Now integrate sine. Now the way I tend to remember it is through the acronym sine. Each letter sine integrates negative. Okay, so when I integrate sine, I get a minus sign, so that's going to be minus cos x. Integrate cos, I get sine. Well, I've still got a minus sign. If I integrate sine, I get minus cos, but I've already got a minus. That gives me a plus cos. And if I could carry on the integration, but actually I'm going to then times it by 0, so I don't need to. So multiplying, going across, gives us our terms for the integral. So I'd have minus x squared cos x. I've got a plus there, but there's a minus there, and I'm times in these. So I've got minus x squared cos x minus 2x times minus sin x, that's plus 2x sin x plus 2 times cos x, that gives me plus 2 cos x, and plus c. It's an indefinite integral. So that's a really kind of short way of doing it, and I'm going to show you the standard way using the formula, and we can see, well, I can check that I get the same answer. So we'll just scribble the formula around here. So we've got u dv dx is equal to uv minus the integral v du dx is quite helpful to do a bit of self-talk, talk to yourself as you say the formula, won't you remember it a bit easier, not if you need to anyway. So u is equal to x squared. If I differentiate that, I get 2x. dv by dx, which is the other part of the product, is going to be sin x. So v is equal to minus cos x. Now, using the formula, so we're going to have the integral x squared sin x dx equal to uv, times those things together, so minus x squared cos x minus the integral of these two things times together. Now, because we've got a minus there, I'm going to put plus. So plus 2x cos x dx there. However, I now have another product, 2x cos x, that's a product of 2x and cos x, so I'm going to have to do the same thing again. Now I've got algebra and trig, so I'm going to say that u equal 2x dv by dx equals cos x. Differentiate this one, du by dx is 2, integrate this one, get sin x. So I'm going to keep the whole integral in here. I get minus x squared cos x plus, now this part is going to now be uv, 2x sin x minus integral of these two things, the integral of 2 sin x dx. Okay, and then I can evaluate it because I now no longer have any products. I know sine integrates the minus cos, so I'm going to get plus 2 cos x plus c. So that's quite clear two examples of how to use both the formula and the DI method. As you see, the DI method appears a lot shorter. It's a bit easier to make mistakes with if you don't remember the pluses and minuses that are on the side here. Okay, so you can easily get a sign error. You can always check by differentiating, so if you did make a mistake, that'll be a way of checking. But for this is much clearer and easier to read, and quite a simple process, and for a lot of the examples that you'll need it for, it's actually absolutely fine. So we'll do another one. I'm going to show you both methods, and then we'll think about where the limitations of each method might be. So if I've got x to the 5 e to the 2x, so if I look back at this previous example, I had x squared. Now what I was essentially doing was I was differentiating the x squared until I got to 2. Same on this tabular method. So in this one I've got x to the 5. So I'd have to do 5 applications of integration by parts. I'd have to keep repeating and repeating it. So probably using the formula isn't going to be the best way of doing it. I'm going to end up with a lot of work. So this is one where it's actually favourable to do it by the DI method. So again, thinking about Lie8, I'm going to differentiate the x to the 5, integrate e to the 2x. So I can just focus on differentiating. Right. So that's all I've done. Then I can just focus on integrating. So e to the 2x, remembering that number comes down one fraction. 2x, 32 e to the 2x. That's just going to be careful of making everything aligned. Okay, so then we've got to remember our plus, minus, plus, minus, plus, minus, plus. Then we're going diagonally across, and we're multiplying those terms together, including the sign in front of it. So the integral, I'm going to write at the bottom, just going to take a lot of space. It's going to be a half e to the 2x. We tend to, whenever we write some of the exponentials, we tend to write the number, then the bit of algebra, then the exponential parts, and trig tends to be the rough order and that we tend to write things. So do try and keep it in that order. It makes it cleaner if you're consistent, rather than having sort of e to the x cos x and then cos x times x squared, and it makes it easy to read if you're not putting brackets around, for example, cos x. So here I've got the half first, and then I've got x to the 5, I've got e to the 2x, and I've got a minus 5 quarters, x to the 4, e to the 2x, plus 20 over 8, you could simplify, I'm not going to here, x cubed e to the 2x, got a minus 60 over 16, again which can be simplified, x squared e to the 2x, plus 120 over 32, x e to the 2x, minus 120 over 64, e to the 2x, plus c, and everything else will go because we get 0 there. So that would be that integral. You can check it either online or check it by differentiating it. I'll give you x to the 5, e to the 2x, but that would become a very messy process if you were to do that by hand using the formula. DI method's much better here. Right. Now let's look at this example. We've got e to the x sine x. This is quite a complicated integral, so we'll think about, we could have this one, so let's try di. So we have Li8 to get us started, Liate, so we've got trig and exponential, so we'll differentiate sine x, integrate e to the x, differentiate sine, you get cos, differentiate cos, you get minus sine, differentiate minus sine, you get minus cos, differentiate cos, you get sine x. You might start to see part of the problem here now, because I'm just going to get an infinite loop of sine cos minus cos, and just loads of ETXs going down this side. So there's a problem here. I'm not going to be able to do it using this method. Previous methods, we ended up with 0 at some point at the end of the differentiation call. Right, whereas it's not happened here, so that's going to be, well, we can't do it this method. Let's try and see if we can do it a different method. So let's try and do our normal way of our formula. Okay. So let's try u is equal to sine x is dv by dx is e to the x, u by dx is cos x, b to e to the x. So I'll get e to the x sine x is equal to uv e to the x sine x minus the integral of e to the x cos x. Okay, now let's think about getting, well, let's e to the x cos x and see what I can do with that. So I could say u is cos x. It would be pointless me saying u is e to the x because I'll end up just looping back. dv by dx will be e to the x again. So b is e to the x. If differentiate cos, I get minus sine. So I'm going to have e to the x sine x minus, I've got brackets, so I have to set the minus, uv minus the integral of those two things times together. Now I've got a minus here, so I'm going to have plus. So I've got e to the x sine x dx, let's expand that. So e to the x sine x minus e to the x cos x minus the integral of e to the x sine x dx, which was our original integral. Seem to go back to where we started, but actually that's quite helpful, because if I add this integral to both sides, that'll cancel with the integral here on this side, and I'll have 2 on this side. So 2e to the x sine x equal to e to the x sine x minus e to the x cos x. Technically plus some constant. So I can now rearrange it. Just need to divide by 2. And e to the x sine x dx is just simply going to be e to the x sine x minus e to the x cos x all over 2 plus c. I know it's not put a dash, it's because I'm being a bit lazy in terms of if I divide that by 2, I'll get a new I'll get c dash over 2, which is just another constant. But that's the integral. Okay, which would have proven impossible using the DI method. So there are certain integrals that if you do the DI method you cannot do. So using the formula is quite a safe point, quite reliable in terms of you can apply that and you will get somewhere. However, with ones like this one, it's going to take a very long time for you to actually work it out. So this is a standard one. So if you ever got an exponential with a sine or a cosine, this will always happen, and this is how you tend to solve it. You just have to use a bit of algebra and rearrange equations. If you're struggling with this step here, you could say call each bit, we tend to call it I. You could call it any letter. And substitute that into there, you get an equation. You get I equals something, take away I, so then 2I equals that, divided by 2. That's another way of thinking about it. But that's a very challenging integral, and that's the standard way of solving it. Right, let's have a look at this integral. Integral of log. So we know if we differentiate log, I get 1 over x. What if we integrate log? What do I get? We don't know. You might not have been told. You might have been told. Might have memorised it. Might not have. But you might be thinking, why on earth is this coming up with integration by parts? Now, one trick we have, if we ever want to integrate any inverse function, I'm going to rewrite this integral as 1 times, sometimes using dots mean times, log x dx. You might think, well, how on earth does that help? I'm going to apply integration by parts to these things. Now, remember Light, we would always say u is log x, so that means the other thing has to be 1. du by dx is equal to 1 over x, b is equal to x. So this is going to be uv x log x minus the integral times those two things together. But 1 over x times x, that's just 1. You get x log x minus x c. And that's the integral of log. So it's just a trick. It doesn't work for, well, you can do it with other functions, but it particularly works well with inverse functions. If I were to differentiate my answer to check, I've got x log x minus x plus c. Okay, x log x is a product, so if I differentiate the x first to get log x, if I differentiate then the log x, I'm going to get x times 1 over x minus x plus c. Need to differentiate x, minus 1. Need to differentiate c, that goes away. So I get log x plus 1 minus 1 equals log x. That works. I could do it the DI way. Let's see how it goes. So I need to remember that differentiating log, and I'm integrating 1. So 1 over x, if I was differentiating that, I'd get minus 1 over x squared. If I was integrating that, I'd get x squared over 2. So it doesn't seem that it works because it doesn't seem to end, although if you know a bit of further maths, it does relate to the power series definition. Vlog, I believe you'd get the term, each of the terms out of there. But this is a good example where the DI method falls short onto the formula method. You could write with inverse tan, depending if you know what the derivative of the inverse tan is. So I'm going to write this as 1 times tan inverse of x dx. So you'd say u is inverse tan of x, dv by dx is equal to 1, du by dx is 1 over 1 plus x squared, and v is equal to x. Right, I can either that's given in most formula books, or you can know that you can use the inverse use the inverse function rule for differentiation. Now let's say y was tan inverse x, and I could say that tan y is equal to x. So if I want to find dx by dy, what's tan differentiate to? Well, it differentiates to sec squared. Now if you've got sec squared, we've got a rule that's 1 plus tan squared. So tan differentiates to 1 plus tan squared. And well, that's just what x is. So 1 plus x squared is dx by dy. So if I want dy by dx, it's just a reciprocal 1 over 1 plus x squared. That's just the sidebar. Let's try and do this integral. So it'll be uv x tan inverse of x minus the integral, those two things together, x over 1 plus x squared. And then actually, if you notice, the bottom almost differentiates to the top. It differentiates to 2x, so if I do that, that makes it work. So I've got minus a half log at the bottom bit. See? And you can see how that 1 plus x squared term's actually in the derivative of inverse tan. So, overall, just to summarise, got a few different points to make. So we've shown the formula method for integration by parts, more reliable, so pretty much every integral that you can do, you could use by parts and it might help. So more reliable, and you're given the formula in most exams. Or it's easy to make mistakes with minus signs, particularly this minus sign here can be a burden to a lot of people. And also if you've got lots of repeated integration by parts, it can be very lengthy and again very easy to make a mistake with minus signs. Tabular method, so it's very sort of easy and neat to do. It doesn't work for all integrals though, and you need to remember these signs at the start or else you'll get those wrong. So two different methods of integration by parts. What I tend to do is I tend to use the DI method if I know it's one that doesn't require any repeats, or if it's an inverse one. But if I get stuck using that method, I will also use the formula. So it's important to not just stick with one and practice that one. If you want to use the DI method, it's important that you do also practice the formula, just in case that you need it. So do give both those methods a bit of practice, both very useful, depending on the circumstances. Thank you very much for your time.